So what I want to do is an example on how this is codified in Excel software. And in the Excel software, Visual Basic was used with a macro. But really, what we're trying to do is, given the ply stacking sequence and the properties of every ply, so E11, E22, and so forth, come up with the laminate engineering constants, EXX, EYY, EZZ, and so forth. Instead of having to test every single configuration of ply stacking sequences, you can come up with a code that tries to approximate that behavior. I have an Excel sheet that basically goes into that. It implements the lecture number 3 from the video and attempts to come up with those properties, effective properties for a laminate. Here you can see that for 6 different material are provided. AS4 8552 unidirectional and so forth. You can see here for plane weave that E11 equals E22. We expected that. We should know that that should happen. And here you can see that the properties are given for all of these different materials here. Now you can see some errors, for example, and that's on purpose to make you think about what's going on here. AS4 8552 unidirectional. I'll have expected nu12 to be equal to nu13 because 1 is the fiber direction, 2 and 3 are the matrix direction. So this should be more like 0.3 as an example. G12 should be equal to G13 because it's unidirectional. And so the 1 is a fiber orientation, 2 is a matrix orientation. So G12 should be equal to G13. So that was done on purpose again, just so that you can see how this works. I'll let you figure out whether the rest of them are correct. But the bottom line, the way this works is, here's your information for the different material properties. And then you come here and you say, okay, I have 20 plies. I have 20 plies. The materials IDs are given here. And so that's selecting material ID carbon epoxy. Sorry, I apologize. And so then the cure thickness is provided here. It's in a smaller end, but that's okay. This is just every ply is the same thickness basically, so it doesn't matter. And here you provide the ply angles of the stacking sequence. Recall that the first ply is always against the tool direction. Sorry about that. And I'll hit here, calculate homogeneous properties, and the Excel sheet will then use Visual Basic to calculate EXX, EYY, EZZ, nu XY, nu YZ, and so forth. It gives you all the properties, including the shear coupling coefficients that we talked about. In this case, they're close to 0. It can also provide, if you hit here or click here, it can provide an Abacus input deck so you can enter directly the engineering concept. So let me explain again why it is so convenient to look at. Going here, say that I have a finite element model that's highly complex and it has many plies, maybe 80 plies. I'm very interested in what's going on at the very top where maybe there's a wrinkle in the composite. Well, I don't want to model every single ply because that'll be computationally expensive. If I have to represent every ply with a mesh line, that'll be a huge model. Instead, you can take a stack of plies at the bottom, and you can see I have a single line of elements, single row of elements. I can just take that, and maybe that's representative of, say, 75 plies. And I can come up with effective engineering constants for those 75 plies and not have to model every single ply. I'm modeling the effects, right? Just the effects. Well, the top 4 plies are important because that's near where the wrinkle is. And so that's going to increase efficiency by a factor of 10 in this example. Here's another example of that, and I can go on and on and on. The bottom face sheet in this case was a single row of elements, and it was approximated with engineering constants the way I've explained it. So going here again, if I click on any of this for Nastran or Abacus, it will then generate a card they can input directly into your code. This code can also tackle, so say I want to do 15 plies instead. So let's do 15 plies. And I want to do, I want to do material ID 1. Maybe I want to combine some of them. So I'll do a hybrid system instead. See what happens, right? And I want to change the ply stacking sequence to be 45, minus 45, 90, and 0. Okay. Which could be quasi-isotropic. It's not quasi-isotropic, but it could be. And I'll just paste this over here. Okay. Then this can also tackle multiple material properties. So here I'm selecting from AS48552 unidirectional. And then I'm selecting for carbon epoxy AS43501. So I'll then just go ahead here and hit calculate. And it should, in theory, calculate all these properties. You can see them here. It gave me a shear coupling coefficient close to 0. It gave me the modulus, right? We can make it all the same material ID as well. And the answer should change when I do that. You can see the Poisson ratios are very close to each other, which makes sense because it's going to act almost homogeneous. Yeah, so this demonstrates the use of this code, which I'll be providing to you. And you can actually change the ply angles. You can look at different configurations. You can check different combinations to see what will happen. And you can use this for tailoring to get the best properties you want for that particular application.